Now we study the Riemann integral. This is chapter 7, section 7.2. We're going to be defining the Riemann integral. So here, the theory of Riemann integrability was developed by Riemann, followed by subsequent work by Darboux to formalize things a little bit more. There are other ways of defining a notion of integral for a function that allows for more exotic functions to have an integral. So I mean, this is what we'll discuss at the end. But for now, it is important to have some intuition about what we mean here. So perhaps you remember from Calc 1, no, Calc 2 now, depends on where you took calculus. You try to define the integral from a point A to a point B by making subdivisions here and you consider these rectangles here. And if you added the areas of all these rectangles, then you would obtain an approximation of the integral. In fact, well, then you probably heard about, I mean, many times when you hear your teachers talk about the area under the curve, or the sine area under the curve. But in fact, this is kind of an incorrect way of viewing things, because in fact, the theory of Riemann integral, I mean, or integral, any theory for that matter, for integrability, allows you to define the area, the notion of area. So it's not that you're proving that the integral converges to something if you haven't defined that something to begin with. You cannot say that actually is equal to the area when you have not defined the area. Whole point of the theory of, I mean, the theories of integral and the definitions of integrals for different kinds of functions is intimately linked with the notion of area or measure or some sort of, I mean, some notions that would extend the notion of areas for simple functions. And so, what do I mean by that? So you have a notion of an integral if so you have a kind of an acceptable notion for an integral if your notion agrees on all functions for which you already know what the area under the curve is. So you should agree on those, and should also extend the notion to other functions that cannot come from, you know, like rectangles, triangles, and stuff like that. And he has to do so in a consistent way. So if you try to compute integrals of two objects, and if you get, for instance, that say this function here has smaller integral than this one, for instance, between the point A and B, then your theory is not good, because I mean it doesn't extend also the notion that if a function lies above another one, then the integral should be bigger. But also matters of inconsistency. If you try to compute the integral following two different procedures, and which is actually what, I mean, I kind of got sidetracked by that, with that. But if you try to define the integral in such a way that allows you to compute the integral in two different ways, and you obtain different answers. So for instance, with one approximation, instead of approximation, you would obtain a certain limit, say 5 and another using another one you obtain 1, then your notion is not good. You should, I mean, the value should not depend on the kind of approximation you're using, and that's a matter of consistency. You're using the rules or the properties of your in your theory for the properties that allow you to define integrals should be such that you get consistent answers, not only for the same function but across different functions. So you cannot contradict I mean your intuition and the notions you already know for simple shapes, for straight lines or stuff like that, constant functions and such. So that in mind, so for Riemann, starting point is the notion of partitions, and associated to partitions there will be upper and lower sums. So the definition 7.2.1, a partition P of A, comma B is a finite set of points x0, x0, which is equal to A, starting from A, and where x0 is less than some x1, smaller number up to xn, which is equal to B, to the other endpoint. So now, for each subinterval x of I minus 1, comma x of I of P, we let m's of k, little m's of k, the infimum of f of x such that x is in this interval. Okay, so I should probably use stick to all k's or to all i's. Isn't there more k's? So I'm just gonna use all k's in here. You have the infimum of all the values of f inside this closed interval, and capital MK is going to be the supremum of f inside that closed interval. So now you may ask, why is it they were considering the infimum or the supremum and not just the max and min? Well, the function need not be continuous, and that's I mean, the functions that are integrable are not necessarily Riemann integrable are not necessarily continuous. Of course, if the function f in question was continuous, then this would be a max. This infimum would be a max actually. Why is that? I'll give you some time to think about that. So the supremum and infimum here can be turned into max, simply because we know that this closed interval, since it's bounded and it's closed, is a compact set. And if you have a function f defined, a continuous function f defined in a compact set, then it attains its minimum and maximum. Hope you remember that from previous module. So now with this hand lower sum of f with respect to p is given by L f comma p just the sum from k equals 1 to n of this small mk times xk minus xk minus 1. So locally, if this is, say, xk minus 1 and xk, you're adding this small rectangles, the areas of the small rectangles. So this would be, in this case, I mean the infimum is attained, and this value here is m sub k. Now the upper sum is in the same way. The upper sum is defined, again, that depends on p as well. The sum from k equals 1 to up to n, capital M k, times xk minus x sub k minus 1. So in this case, instead of adding the areas of the small rectangles inside this interval, the maximum is at the other endpoint. So this would be mk, capital MK, and this would be your you would be adding the areas of these rectangles that lie above the function f. Even when you're dealing with continuous functions, the max and the mean may not be attained at the endpoints. This is just something special about this drawing, this example. So for instance, if you have something like that, then the min can be attained perhaps at one of the endpoints. So let me draw this again. But the maximum is it's attained at some point in between. So in that case, this would be capital M sub k. And while this would be little m sub k. So again, even when we have continuous functions, and so that the supremum and infimum are attained inside the interval, the maximum or minimum need not be attained at the endpoints. Okay, but the upper sums and lower sums are defined like this. So so you're adding either smaller rectangles or bigger rectangles. So rectangles that lie above the function or below the function. So something that is clear is that u of f comma p is always greater than or equal to L of f comma p. A very important thing. So here, of course, I mean, it's important to see the notions of refinement, for instance. So partition Q is a refinement of a partition P if P is contained within Q. If Q has more points than P, that is. So you have more divisions in your refinement than for the original P. Now, lemma 7.2.3 tells you that if you have a refinement, then what you expect, of course, will happen. That is that if P is contained within Q, I mean, meaning that Q refines a refinement of P, then what do you think will happen to the lower sum? The lower sum of the refinement is going to be at least as big as the lower sum for the original partition. And the opposite is going to happen for the corresponding upper sums, for the upper sum. So what am I drawing here? Graphically, it's kind of clear if you think about it. Suppose you have a function like this, and you consider a very rough partition. It only has two terms, so this is x0, this is x1. Then the upper sum associated to this partition will be the area of this big rectangle. If you pick any point in the middle instead, then the corresponding upper sum will be the sum of this area plus the sum of this area. Sorry that I But of course, the sum of these two the areas of these two rectangles is smaller than the area of the bigger rectangle. So the upper sum of the refinement is smaller than the upper sum of the original partition. So for the original partition, this would be x1, x1, and this would be x2. Well, for the refinement, this would be x1, and this would be x2. x1 is the middle point, and x2 is now the end point. Previously x1 for the original partition, now it's x2 for the refinement. So this is the content of this lemma, but this is just a routine kind of proof. So I'm leaving it up to you as an exercise. I mean, to verify and to read. What is about. I'm not going to ask you actually to prove anything related to that. Now, the next thing that we need to know before defining the integral P1 and P2 are any two partitions. Any two partitions of the interval a comma b then what do you think is going to happen? I mean, if you try to compare the lower sum and upper sum of any of them, I mean, it doesn't matter. One could be one could be a refinement of the other. I mean, it doesn't matter. No matter how, I mean, what two partitions you choose, if you compute the lower sum of one and the upper sum of the other, what's going to happen is they're going to be ordered. So the lower sum of f comma p1 is less than or equal to the upper sum of f comma p2, u of f comma p2, so the upper sum for the other partition. In fact, you can switch the roles here of 1 and 2 because these two partitions are arbitrary. So what this tells you is that you can never have you can never have a lower sum be greater than any upper sum. And the proof is actually quite simple. So if you can define a common refinement, so you can take the union of the points P1 and P2, and the lower sum of f and P1 is going to be less than or equal to the lower sum of f and q because of the previous lemma, and then that's going to be smaller than or equal to the upper sum of f comma q because of the lemma before that one, and that's going to be less than the upper sum of f comma p2 because your q is going to be a refinement of p2. It's going to be a refinement of p1 and p2. So combining the two previous lemmas, you obtain this. So naturally, what you expect is if you get refinement, more refinements, and more refinements in these two numbers here, you get closer and closer. That could be a good candidate for the integral of f between a and b. And in fact, this is the way you define it. So when that limit, it's always here in analysis when when you can define something, when something has a limit, then it's a well-defined notion, so it's independent of the choice of a sequence or partitions or whatever you want to call it, or whatever you want to do with it. I mean, these lower sums or upper sums. If there's something that is well defined, it doesn't depend on the approximating objects, then because there's a limit, then you have a well-defined object, which in this case will correspond to what we'll call the Riemann integral of f between a and b. Okay, so now we are ready to define the Riemann integral. So let telegraphic P be the collection of all possible partitions So you consider any partition of of the set A, I mean of the interval AB, that will be inside P. And what are things that are always well defined? Well, the notion, I mean the supremum of a bounded set and the infimum of a set bounded from below, those are well defined notions. And that's what we're going to use to define just the upper integral of lower integral. So here, the upper integral of f is just the infimum. Remember that if we consider partitions, what happens to the upper sum? They get smaller. So we're going to take the infimum of the upper sums for all, I mean the infimum over all partitions. The lower integral is in turn defined by the supremum, because remember we have see again where I'm starting to get the same problems before for erasing. And we're using the supremum here because we know that lower sums get bigger when we consider refinements. So we have two numbers here. So now we're taking the infimum over all upper sums and the supremum over all lower sums for all partitions. And so what? I mean, clearly by all the properties we've seen before, we know that u of f will then be greater than or equal to L of f. So that's true, I mean, for any function. Now, when will we be able to say that the function is Riemann integrable?